Hello and welcome. In this video, we're going to look at how to calculate this RLC parallel band pass filter. In this case, we've got a parallel on this top bar here, so our input voltage comes in and it goes in parallel. So some can go across the capacitor, whatever's allowable, and the rest can go across the inductor down here, whatever's allowable, which means that we're going to allow certain frequencies to output instead of that series component one where we stop frequencies from outputting. So in this case, we're going to go after our frequency first, and they make it extra hard here because they want the exact center frequency, which means we need to include every piece of our winding resistance in our calculation. And so that's going to require that really long frequency equation. So our FC is equal to, usually we put 1 over 2 pi with our time constant, but in this case we need to include our winding resistance, so we'll put that square root of 1 minus our winding resistance, RW squared, multiplied by our capacitor, divided by our inductor, and then that entire thing gets divided by 2 pi, square root of our LC for our time constant. All right, so that's the equation we're going to plug into. We have all of those values already, and so we can just go directly to our calculator and start plugging that in. We'll do the square root equation first. 1 minus, we'll open parenthesis, and we want our winding resistance squared. Our winding resistance is 9.1. We'll square that and multiply it by our capacitor. Our capacitor is pretty small, 180 times 10 to the negative. And we are at pico, so it'll be 12. Right? And that whole thing, we'll close that parenthesis so that we can divide this, just that upper half, by our inductor of 7.5 micro. So 7.5 times 10 to the negative 6. Oh, I didn't miss that negative there. To the negative 6. Okay. And then after that, we'll go out to the outside of this square root equation and we'll do another divide, and that'll take that entire thing, put it on top, and then we'll put in our 2 pi times our square root of LC. So 7.5 times 10 to the negative 6. And then that is multiplied by our capacitor value of 180 times 10 to the negative 12. So that is our output that we expected there. So we'll set this equal to, so our frequency, they want it in kilohertz here. We got quite a large number here. Make sure we typed all of our equation in correctly. Looks like it. So we'll put in 4, 3, 2, 7, 3, 4, 2. We want to move it into kilohertz, so we'll take our decimal location, move it forward 1, 2, 3 spots there, and put our decimal point there, and that's our new number. And so we'll say that we have 4,327 kilohertz. And that's what our frequency is, so we'll plug that in for our frequency down here, 4327. Our bandwidth is dependent on our components in the circuit, and so let's write in our bandwidth equation and then how we're going to get to that equation because we don't have what we need for it. Bandwidth is equal to our Q factor and our FR, so our frequency at resonance divided by our Q. We don't have our Q, we just got our frequency up here. That's our cutoff frequency at the top here. And so we'll start with our Q. Our Q value is our components, right? It depends on our inductor and our resistors in the circuit. So we'll say Q is equal to our XL divided by our RW, right? Our winding resistance. That's what we're going to use for this. We're not using the load for this one. In the series one, you would use the load with it. And so in this case, so we'll do our XL on top. We don't have our XL, right? So let's do that first. So let's go XL is equal to 2 pi, our frequency that we just found, and our inductor value. And so we can find that first, and we'll say that 2 pi times our frequency, which is quite large. So we'll say 4327000, and that's our full value for that. And then we'll multiply that by our inductor value of 7.5 times 10 to the negative 6. And that gets us a 204, we'll round that up, 204 ohms, right? It's not in kilo ohms or anything, it's just in ohms. So after that, we can plug into our Q. We can say 204 divided by our winding resistance of 9.1. That gets us our Q output. Say 204 divided by 9.1. 22.4 is our Q. So now we can set that out. So 22.4. That is just a factor, so it has no ending on it. And so now we can go down to our bandwidth equation. And we can set this equal to our resonant frequency on top, 4327000, divided by our 22.4 for our Q value. We'll set that out. 4327000 divided by 22.4. It's us a large number there, so that's our bandwidth. It's 193,169. We can move that forward by 3 and round it off. So we'll say 193 kilohertz. We'll plug that in. That's our next value, 193. Now they want our output maximum for our voltage and our minimum voltage. So let's do that next. We'll change our color one more time. So with this one, we want to go after our maximum output first. We'll calculate that out. That's just basically our voltage divider equation again. And so we'll take our load into account with this one. So let's do V out max is equal to voltage divider. So we know that our maximum output is going to be dropped across our load out here. So what we want goes on top as our R load. And what we have goes on bottom, and that's going to be our Z, essentially, because we have to account for the winding resistance as well as our inductor. We know that our L and our C at resonance are going to cancel each other out. So we have our load resistor, RL, 80, and added to our winding resistance, RW. And then that whole thing gets multiplied by our input voltage. Right, so this will be the maximum output that we can have, is when L and R are completely canceling each other out and all we're left with are linear components. We'll set that out. So our load resistor is 510, and that's on top of our voltage divider, multiplied or divided by our 510 plus our winding resistance of 9.1. That whole thing gets multiplied by our input voltage of 10. So 9.82 is going to be the maximum voltage when everything is completely linear. 9.82 volts. And so that's our first answer there, 9.82. And then we are going to do the other one, which involves our Q for it. So we need to know what our maximum resistance would be, worst case scenario, right? So that's going to give us our lowest output that we can have. So in this case, our V out minimum is going to equal our load divided by our total reactance again. So RL divided by our R load added to our Z total, right? Because before we said, well, if it's fully linear, it's just going to be the winding resistance left over. But if it's not fully linear and they're out of, they're at their maximum quality, that's going to give a different range, right? So now we need to figure out what our ZT is so that we can apply this voltage divider equation. And our ZT at this point will be our Q factor plus 1. So there's a new equation that we're going to use for this one. Our Z for our maximum resistance, including our winding resistance. So RW is our winding resistance, and that's dependent on our quality. And so we'll say that it's our Q squared plus 1. Right, and that's going to kind of give us the full range of that quality that we talked about. So this is where it comes into play for our components. So RW, winding resistance, is 9.1, and we'll multiply that, using parentheses here, by our Q factor, which was 22.4 squared. Add that to 1. And that just makes it on the positive side. And so that gives us a maximum of 4,500 575 ohms, right? That's a factor of our resistance for our winding resistance. And so we're going to use that as our ZT in this equation. Let's keep going here. So we'll plug it into our voltage divider. We'll send this out and we have everything we need for that. So that's that 510 on top divided by 510. 510 plus our new value that we just got for that maximum 4575. Then that whole thing gets multiplied by our voltage, which was 10 volts. So 1. At minimum, we're going to have 1 volt drop. At maximum, we're going to have all the voltage drop. All right, so let's check our output here. There we go. Okay, let us know if you guys have any questions.